Welcome back to Limits in Calculus. In this video, we're going to go over limits of exponential functions. Okay, my name is Kevin Tokoph. Make sure to like this video and subscribe to the channel for future videos and notifications. All right, so when we're dealing with exponential limits, I would recommend that you go and watch the video if you haven't already of how to deal with infinite limits. So that's limits where x or whatever variable we're using goes to infinity or negative infinity. Because in general, exponential limits for the most part are really most useful there when we're approaching infinity or negative infinity. And that's just because if I were to take e to, like if I was saying x goes to 4, what is e to the 4th? I don't know. I mean, occasionally something like that can crop up. But generally, when we're looking at exponential functions, we want to look at the behavior as x just goes off to infinity in either direction. That's generally what we want to do. All right. And that just has to do with more of like it's more of a physics thing as to why it's more applicable. Anyways, this right here, this first graph, this is actually a graph of the function e to the x. So y is equal to e to the x. All right. And there's several important things about e to the x, right? Number one, what I'm going to do very quickly is I'm going to show you right here at this point. This is where e to the x crosses the y-axis. And it always crosses the y-axis, no matter what form of e to the x is. It crosses at x equals 0 and y equals 1. So when x is equal to 0, e to the x crosses the y-axis, and it crosses specifically at y equals 1. All right? And it sort of just looks like this. This is what the general function looks like. Okay? E to the x, as x gets more and more negative, as you go farther and farther on the x-axis, you can see that e to the x gets closer and closer to y equals 0. Like it's approaching the x-axis, it's approaching 0, all right? But e to the x can never be negative, meaning e to the x can never be in this area down there. Okay, it's never below the x-axis, meaning the value of e to the x is never negative, all right? It's always positive. Now, if you go in the positive direction on the x-axis, notice that e to the x keeps getting larger and larger. Okay, so what we're going to do is we're going to define some fundamental limits for any e to the x based function. All right, so this could be e to the x, e to the 2x, e to the 3x, and so forth. All right, if we take the limit of e to the x as x goes to 0, this is equal to 1. Why? Because when we plug in e to the 0, when we plug in 0 for x, e to the 0 is 1. That just means that when x is 0, right here, y is 1. And that's just because it crosses the y-axis when x is equal to 0, and it crosses at y equals 1. All right, the limit as x goes to infinity. Well, that means x is going farther and farther to the right on the x-axis. And you can see, hopefully, that e to the x is going to get larger and larger and larger, and it's never going to stop growing. So as you go to the infinity on the x-axis in the right direction, limit as x goes to infinity of e to the x is just infinity. All right? Now, one thing I said is when you go to more and more negative values of x, this function gets really, really close to to the x-axis, to y equals 0. It never actually hits the x-axis. It gets closer and closer and closer, but we would say that as x goes to negative infinity, e to the x is basically 0, okay? When we're talking about limits, remember we're saying the function approaches this value. In fact, for exponential function e to the x, it can never equal 0. But as you go to negative infinity, as this x gets larger and larger in the negative direction, we say that it basically is 0, right? Now, another kind of function that crops up a lot is what if you have e to the negative x? How do you deal with that? Well, essentially all we're doing here is we flipped e to the x across the y-axis because it's e to the minus x. Well, if we take e to the minus x and plug in 0 for x, so the limit as x goes to 0, it's also equal to 1. Why is that? Well, that's just because it still crosses the y-axis at the same point, 0, 1, exactly the same point. Okay? Now, for this function e to the minus x, if we take the limit as x goes to infinity, so positive infinity, it's getting farther and farther to the right, notice that this function is going to get closer and closer to 0 as x goes to infinity. All right? So if we do that, if we plug in infinity for x, it's essentially e to the minus infinity, and that's just 0. Notice it's approaching 0. However, if we take the limit as x goes to minus infinity of e to the minus x, so we're getting farther and farther in the negative x direction, notice that this function is actually going to blow up really quickly, and it's essentially going to go to infinity. All right? So one way to think about this is if you're given a function like e to the x, okay, let's say you have e to the minus x. And let's say you're going to evaluate this as x goes to infinity. One way to think about this is just to literally plug in for x infinity. So I have to keep the minus sign, but then I throw in an infinity there. What's e to the minus infinity? Well, e to the minus infinity we said was 0, right? Because when you plug in negative infinity for x, it's 0. So this is 0. But what if you have something like limit as x goes to minus infinity of e to the minus x? Well, really all you do for this is you say, well, this is e to the minus, and then plug in minus infinity. Well, the minus is canceled, and you're just left with e to the infinity, which we said was infinity. All right? So you can sort of think about it by just plugging whatever the limit is in, but you have to make sure to keep all the minus signs and cancel them as appropriate. Okay? So hopefully that made a little bit of sense. And that's just basically the general kind of limits that we're going to evaluate for exponential functions. So here we're going to do some examples just to get a grasp on it, because the best way to do this is just to do examples. Let's look at the limit as x goes to infinity of 4e to the 2x divided by e to the 4x. All right, so these at first can actually be kind of imposing problems, but let's break it down. All right, so the way these exponential functions work is the following. So we have 4e to the 2x. One thing to keep in mind is, let's suppose I do have e to the 5x. Okay, I'm going to use a different number than here. If I have e to the 5x, technically this is e to the 2x times e to the 3x. And the way to kind of think about that is I have a 5 right here, right? I have a 5. Here's a 2 and this is a 3. So if I had 2 plus 3, that has to equal 5 as long as x, and x are the same. So e to the 5x equals e to the 2x times e to the 3x. Another example is if I have e to the 7x, this is equal to, what's one way I could make 7? Well, I could have 4 plus 3. So, because 7 is equal to 4 plus 3. So this is equal to e to the 4x times e to the 3x. I could also write this, say, as e to the 1x times e to the 6x, right? There's different ways I could make this, but it's going to be really important to look to see what cancels in the particular problem that you're dealing with. All right, so let me write that a little bit neater. So I have 4e to the 2x divided by e to the 4x. Well, I want to essentially cancel this e to the 2x in the numerator. So this e to the 4x, I can break it up into e to the 2x times e to the 2x. And that's perfectly legal. That's one of the exponential rules that you'll learn about in a later chapter. So this is as x goes to infinity. Well, notice I have an e to the 2x divided by e to the 2x. So those cancel. And then my limit becomes the limit as x goes to infinity of 4 over e to the 2x. All right? Now, the way to think about this is sort of to treat the e to the x's sort of by themselves. All right, imagine it's not in the denominator. Imagine you're just evaluating as x goes to infinity e to the 2x. So I'm only concerned about this for now. All right, just that part right there. What is e to the 2x if I plug in x as infinity? Well, that's just equal to, essentially, it'd be e to the 2 times infinity, right? But that's just e to the infinity, right? I don't care about this 2. Infinity is just infinity. So what's e to the infinity? It's infinity. So the way to think about this is essentially, it's sort of like if you have 4 divided by infinity. Because we just said e to the 2x was infinity, so I'm just going to say this is 4 over infinity, okay? Now technically this is not a correct way to write this, but when you evaluate this, it's essentially 4 divided by infinity, and anything divided by infinity is 0, okay? So that's the way to think about these exponential functions. If I have any exponential function, and especially a limit as x goes to infinity or negative infinity, I sort of just treat them independently, not worrying about anything else. And once I have this, remember I had this e to the 2x, I found that was infinity, and so I just say 4 over infinity, but that's just 0. Okay? I'm going to take a similar approach when I do this type of problem. So suppose my problem is now limit as x goes to infinity of 7 times e to the 3 divided by x. So what I'm going to do is I'm going to say, I'm just going to simply take this infinity and plug it in for that x, right? All right. So what is number 1? What is 3 divided by infinity? Well, it's sort of the same thing as 4 divided by infinity. 3 divided by infinity is what? It's just 0. So essentially this limit, since I plug in infinity here, it just becomes 7e to the 0, right? 3 over infinity is 0, so this is just 7 times e to the 0. And what did we say e to the 0 was? If I take e and plug in 0 for x, that's just 1. That's an important thing to remember. So this is just 7 times 1, or just 7. All right? So the nice thing about exponential functions when you're evaluating their limits is whatever is in the exponential function, you can sort of just treat sort of independently, and then whatever thing you get, if it's negative infinity, 0, or infinity, you can just substitute that in for 3 over x or whatever's in there. Let's do another example of this. Suppose I have the limit as x goes to infinity of, this is just some number, k. In fact, just to make this easier for you, k is just a number. Let's just say it's, I don't know, 8, some number. So the limit of x goes to infinity of 8e to the x cubed, all right? So what am I going to do? I'm essentially just going to plug in infinity for x, all right? So what is infinity cubed? It's just infinity, right? Infinity is infinity. I don't care if you cube it, take the square root, it's just infinity. So what is e to the infinity, right? So if I take this infinity now, and this is infinity, so e to the infinity, what is that? E to the infinity is still infinity, right? We said, what did we say? When e goes to infinity, it's infinity. So you basically then have, if this part right here, if e to the x cubed as x goes to infinity, if this part is just infinity, then 8 times infinity is just still infinity, right? 8 times infinity is just infinity, okay? Whenever you have an answer for these limits that is either infinity or negative infinity, all you say is just does not exist. And sometimes people will abbreviate that as DNE. Does not exist. Because really and truly, infinity is not a number. And all infinity is it's specifying where a function is going. Okay, it's used to determine where a function is going if it just goes off forever, basically. Okay, but infinity itself is not a number. So if your limit goes to infinity, we say it does not exist. There's something you'll talk about much later, and depending on where you take calculus, it may crop up. Sometimes you actually just say when it goes to infinity or negative infinity, you say that this limit diverges. Okay, when it diverges, it just means the limit does not exist. Okay, but hopefully this makes a little bit of sense. Let's do one more example, and then we'll do a more challenging type of problem. All right, so here's the limit as x goes to infinity of 6e to the minus 2 over x. So what do? We sort of just imagine plugging in infinity for this x, right? All right, so what happens if we take negative 2 over infinity? Well, it's just over infinity, so it's 0, right? So this becomes 6e to the 0. What did we say e to the 0 was? E to the 0 is just 1. So this is 6 times 1, which is equal to 6. All right? And that's all that limit is right there. However, one of the things that becomes a lot more challenging is if we have limits where it's not just one exponential function, we're taking the limit as x goes to infinity, but it's the sum and difference of several different exponential functions. So suppose I have this limit. Limit as x goes to infinity of e to the 5x plus e to the minus 3x minus e to the 2x divided by e to the 3x minus e to the x plus 4e to the 5x. I'm going to have to plug my laptop in soon. All right, so the way you do this, and this is what you do if the limit for infinity is positive. Notice this is positive. I don't have a negative there. What I want to do if this limit is a positive infinity is I want to look for the numbers here in the exponents like 5x, negative 3x, 2x, and so forth, and I want to find the highest number that's positive. Well, I have 5x minus 3x is negative, 2x, 3x, x, and 5x. Well, certainly the highest number is 5, so I'm going to look at those. Then what I'm going to do is I'm simply going to pull out e to the 5x. In other words, I'm just factoring out e to the 5x in the numerator and e to the 5x in the denominator. Also notice, because I now have e to the 5x over e to the 5x, that cancels because it's just 1. But what happens when I do that? Essentially, the way you can think about it is you're going to just divide every term here by e to the 5x. I'm just dividing every single term here by e to the 5x, all of them. I'm just dividing by e to the 5x, all right? So what is e to the 5x divided by e to the 5x, since I pulled it out in the numerator? Well, that's just 1, right? So what is e to the minus 3x divided by e to the 5x? Well, what you do when you have a quotient like this is you take the number in the numerator, minus 3, and since this 5 is in the denominator, you take negative 3 minus 5. And so that becomes e to the minus 8x. Okay, then I have a minus e to the 2x over e to the 5x. Well, I take this 2 and subtract the 5, and this becomes e to the minus 3x. Now for the denominator, I'm also pulling out e to the 5x. So what is 3 minus 5? Well, that's e to the minus 2x, right? E to the minus 2x. Here I have an e to the 1x. What is 1 minus 5? It's minus 4, e to the minus 4x. And then here I have a 4 e to the 5x. What is 4 e to the 5x divided by e to the 5x? That's just 4. All right? Why do I choose to do this? Notice, I have these numbers here, 1 and 4, but all of these exponents now have a negative power. Negative 8x, negative 3x, negative 2x, negative 4x. What was the limit of those kind of functions when I took it to infinity? What is the limit of e to the minus x? And this could be e to the minus 2x, e to the minus 3x, 4x, whatever. What's the limit as x goes to infinity? It's 0, okay? So now when I come back up here to the problem, anywhere when I take this limit, anywhere I see an e to the negative something x, e to the negative 8x, e to the negative 3x, e to the negative 2x, e to the negative 4x, because the limit's going to infinity, all of these are 0, okay? They're all 0. And so that means I'm going to have remaining at least a 1 here and a 4 in the denominator. So what's the limit equal to? It's 1/4, okay? And that's why I choose to do that. The reason I chose to pull out this e to the 5x from both the numerator and the denominator is simply just because that's going to leave everything else as a negative exponent, and when I take the limit as x goes to infinity, they all go to 0. Okay? Very important point. Now I want to do a similar problem, but instead, I'm now going to take the limit as x goes to negative infinity. All right? So what I'm going to do here is basically a similar thing. Okay? But instead, because it's negative infinity, I'm now going to look at these exponents, and the one with the most negative power is the one that I'm going to pull out. Okay, so what's the most negative power? Well, 4 is not even negative. Minus 2, minus 5, and 1. Well, it turns out minus 5 is the most negative, right? So that means I'm going to divide everything through by e to the minus 5x. So e divided by e to the minus 5x. Divided by e to the minus 5x divided by e to the minus 5x. What is that going to do? Well, number one, here I have e to the 4x divided by e to the minus 5x. So you take this number 4 minus 5, okay? You take 4 minus negative 5, and you get e to the 9x. Okay, notice I have this e to the minus 5x over e to the minus 5x out in front. So this becomes e to the 9x. Then I have this negative 2 minus negative 5. So negative 2 minus negative 5 is positive 3. So this is plus e to the 3x. And if I take this e to the minus 5x divided by e to the minus 5x, they just cancel. So that's 1. Because there's a minus sign here, it becomes minus 1. Then if I take this 2 e to the minus 5x divided by e to the minus 5x, again, the e to the minus 5x's cancel, and so I'm just left with this coefficient 2 right here. And then plus e to the 1x, or excuse me, 4 e to the 1x divided by e to the minus 5x. I do have a 1 there, so what's 1 minus negative 5? That's positive 6, so 4 e to the 6x. Now notice, again, I have this e to the minus 5x over e to the minus 5x, and they cancel because they're the same, right? But I'm taking the limit now as x goes to minus infinity. Why did I choose to do this the way I did? Well, in the previous problem, notice how everything that was left over had a negative exponent, e to the minus 8x and so forth. Here, everything has a positive exponent, e to the 9x, e to the 3x. What happens if I take the limit as e to the x goes to negative infinity? So I have e to the x, and again, this could be, it could be e to the x, e to the 2x, e to the 3x, e to the 4x, e to the 5, 6, 7, whatever. What happens if I take it as x goes to negative infinity? It's 0, okay? So that means, for this limit, this is 0, e to the 9x, this is 0, and that's 0, assuming x is going to minus infinity. And all I'm left with is a minus 1 there and a 2, so this limit is negative 1/2. All right? So that's really important. Sometimes they'll give you these simpler exponential limits to solve that we did first, but sometimes you'll have the sum here, and this is essentially what you have to do. And remember, the key is, if the limit goes to positive infinity, you look for the most positive power of e, and then you just divide everything through by that. In this case, it was 5x, so I took e to the 5x out and have e to the 5x divided by e to the 5x. Okay? If the limit is going to negative infinity, I look for the most negative exponent. In this case, it was negative 5x. So I just pull out an e to the negative 5x divided by e to the negative 5x. And that just means essentially dividing everything in the whole thing by e to the minus 5x. And the reason you do that is just because of the definition of the limits for exponential functions, which were shown here. Remember, if I have e to the positive x and I take it as x goes to infinity, it's infinity. But for e to the x, if I have x going to negative infinity, that's automatically 0, and I'm going to use this to my advantage. Also, if I'm dealing with a negative exponent, when I take e to the negative x and take x going to infinity, this is 0, and I'm going to use that to my advantage. Okay? So hopefully this made sense. This is in general how you deal with exponential limits. In the next video, we're going to go over something called a logarithmic limit. You're going to do logarithms in more detail later on, but it's worth seeing how to deal with them now. So I hope this video helped. Make sure to like the video, subscribe to the channel for future videos and notifications. Thank you very much.